Almost none of your weight is made of anything. Take your body apart. Atoms into nuclei, nuclei into protons and neutrons, protons into the quarks inside them, and then add up the mass of every fundamental piece. You do not get the number on your bathroom scale. You get about 1% of it. In 2012, after a search lasting 48 years, physicists found the Higgs boson, and the world was told they had found the thing that gives everything its mass. But here is what they left out. The Higgs field explains the electron, the individual quarks, and the carriers of the weak force, which together come to roughly 1% of the weight of ordinary matter. The other 99% comes from a completely different broken symmetry, in a different part of physics, that almost nobody has heard of. And underneath both of them sit 4 questions nobody can answer. By the end of tonight, you will know exactly where the explanation stops. Before we begin, if taking one familiar number apart until it stops making sense is how you like to drift off, a like or a subscribe would mean a great deal. It genuinely helps me keep making these. Now, let's begin. There is a number attached to you that you have never once questioned. You know roughly what you weigh. You have known it for most of your life, the way you know your own height or the color of your eyes. It is one of the few facts about your body that can be stated precisely, in a single number, by a machine that costs almost nothing and never argues. Step on, wait a second, read the display. That number has followed you since childhood. It has gone up and it has gone down. You have probably worried about it. You have almost certainly never wondered what it is measuring. And that is fair, because the answer seems obvious. The scale is measuring how much of you there is. It is counting your stuff, bone and water and muscle and fat, all of it added up and reported in kilograms or pounds. More stuff, bigger number. That is what weight means, and there is nothing mysterious about it. Except that when physicists actually did the arithmetic, when they took the particles you are made of, looked up their individual masses in the tables, and added them together, the answer came out wrong. Not slightly wrong, not off by a rounding error, wrong by a factor of about 100. Almost none of your weight is made of anything. I want you to sit with that sentence for a moment, because I am not being poetic, I am being arithmetical. If you take an adult body, break it into atoms, break the atoms into protons and neutrons and electrons, break the protons and neutrons into the quarks that make them up, and then add up the masses of every one of those fundamental pieces, every quark, every electron, every last constituent that the standard model of particle physics recognizes as a thing, you do not get the number on the scale. You get about 1% of it. The other 99% is not particles. It is not substance. It is not stuff, in any sense that would satisfy someone asking what you are made of. It is energy, energy stored in a field, energy of motion, energy locked into a configuration that cannot come apart, and it weighs exactly as much as if it were made of matter, because as far as gravity is concerned, there is no difference. So the number on the scale is real. It is just not measuring what you thought. Tonight I want to walk you through where that number actually comes from, and I want to be honest with you from the start about how this ends. This is not a video where physics has the answer, and I explain it to you, and we both feel satisfied. Physics has 2 answers. Both of them are extraordinary. Both of them are experimentally confirmed to a precision that borders on the absurd. And both of them, when you look at them closely, turn out to be mechanisms without reasons, descriptions of how mass appears that say nothing whatsoever about why. The origin of mass is not a solved problem. It is one of the largest open questions in physics, and the reason most people do not know that is that the small part of it which was solved got an enormous amount of publicity, and the large part that remains open got almost none. Let me give you the shape of what is coming, so you know where we are going. There is a theory called the Standard Model. It is the most precisely tested framework in the history of science. It describes every particle we have ever found, and 3 of the 4 forces that act between them. And in certain calculations, it agrees with experiment to 11 decimal places. It is, by any reasonable measure, the most successful scientific theory ever constructed. And the Standard Model, taken exactly as written, says that nothing has mass. Not the electron, not the quarks, not the particles that carry the weak nuclear force. In its unmodified form, the theory demands that every particle in existence be exactly massless, which would mean every particle moves at the speed of light, which would mean nothing ever stops, nothing ever binds, no atom ever forms, no star ever lights, and there is nobody anywhere to be confused about it. Something had to be added to fix that. What was added is called spontaneous symmetry breaking, and it is one of the strangest ideas anyone has ever had about the universe. It says that the laws of physics can be perfectly symmetric, while the universe they describe is not. That the rules can be balanced, while the world sitting on top of those rules has quietly tipped to one side. The mechanism built on that idea is called the Higgs mechanism, and the particle that confirmed it was found in 2012 after a search lasting nearly half a century. That is the part everybody has heard about. The Higgs field gives things mass. You have seen the headlines. Here is what almost nobody tells you. The Higgs mechanism explains the masses of fundamental particles, and fundamental particles account for roughly 1% of the mass of ordinary matter. The other 99% comes from somewhere else entirely, a second broken symmetry in a completely different part of physics, involving the strong nuclear force and the way it refuses to let quarks escape. That mechanism was worked out separately, verified separately, and it explains 100 times more of your body weight than the Higgs field does. And then, when you have both of those, and you think you have a complete account of mass, you run into the fact that ordinary matter is about 5% of the universe. The rest of the matter out there, the dark matter that outweighs everything we can see by roughly 5 to 1, has mass from no known mechanism at all. There is a detail about the Standard Model that makes all of this sharper, and it is worth knowing before we go any further. The theory contains roughly 19 numbers that it cannot calculate. They are called free parameters, and what that phrase means in practice is that physicists have to go out into the world, measure them, and then type them into the equations by hand. The theory does not derive them. It does not constrain them. It simply requires them as input, the way a recipe requires ingredients it cannot produce. Of those 19 numbers, somewhere between 12 and 13, depending on how you count, are masses, or the couplings that generate masses. Add in what we have learned about neutrinos since the 1990s, and the parameter count rises to somewhere around 26 or 28, and again, most of the additions are mass parameters. Put plainly, the single largest category of things the best theory in physics cannot explain is mass. If someone worked out where those numbers come from, they would not be filling a small gap. They would be removing most of the arbitrariness from our description of reality in one move. So we will go through all of it. What mass actually is, which is not what you were taught. Why the equations forbid it. How physicists broke the symmetry to get it back. What was found under the ground in Switzerland on the 4th of July 2012. Why that discovery, for all its beauty, accounts for less than 1% of you. Where the rest comes from. And then, at the end, the 4 specific places where the explanation runs out. The 4 holes that make this, in my judgment, and in the judgment of a lot of physicists, the biggest unsolved problem in the subject. By the end of tonight, you will know exactly why the origin of mass is still open, and exactly where the answer stops. But we should start somewhere simpler than any of that. Before we can ask where mass comes from, we have to be honest about the fact that most of us have never really examined what the word means. We use it interchangeably with weight, and with heaviness, and with how much stuff there is, and those are 3 different things, and only one of them is what physics is actually talking about. The reason mass is hard to explain is not that the explanation is complicated. It is that the thing being explained is not what people think is being explained. So let us begin by taking the word apart. Pick up something heavy, a book, a bottle, whatever is beside you. Hold it out at arm's length. Two different things are happening in your hand, and physics gives them two different names. The first is that the object is being pulled toward the center of the earth, and your arm is having to push back to stop it falling. That downward pull is weight. Weight is not a property of the object at all. It is a relationship between the object and whatever large body happens to be nearby. Take the same book to the moon, and it weighs about a sixth as much. Take it out to a point far from any star or planet, and it weighs nothing whatsoever. It floats, and you could hold it up with a fingertip forever without getting tired. The second thing is more interesting, and it does not go away when you leave the Earth. Out in deep space, where the book has no weight at all, it still resists being moved. Push it, and it accelerates slowly. Push a pencil with the same force, and the pencil takes off. Get the book moving, and then try to stop it, and you will find that stopping it takes effort, even though nothing is pulling it down. That resistance to being started and stopped is inertia, and the number that quantifies it is mass. Mass is stubbornness. It is the property of not wanting your motion changed. That is the definition physics uses, and it is worth noticing how strange it is. Mass is not defined by what something is made of. It is defined by how it behaves when you push it. Isaac Newton, who put this on a firm footing in 1687, essentially treated mass as a given, a primitive quantity, a number you attach to an object and then use in the equations. His second law says force equals mass times acceleration, which tells you what mass does, but says nothing about what it is or where it came from. For 200 years, that was considered a perfectly acceptable situation. Mass was a fundamental property of matter. Matter was what the universe was made of, and asking where mass came from was like asking where existence came from. It was not a physics question. Then, in 1905, a 26-year-old patent clerk in Bern wrote a 3-page addendum to a paper he had published a few months earlier, and gave it a title in the form of a question: does the inertia of a body depend upon its energy content? His answer, offered tentatively, was that it does. The relationship he derived is the most famous equation in the world, and it is almost universally read in the wrong direction. Energy equals mass times the speed of light squared. Almost everyone reads that left to right. Mass can be converted into energy, which is why nuclear weapons work, and why the sun shines. That reading is correct, and it is also the less important half of the statement. Read it the other way. Mass equals energy divided by the speed of light squared. Energy, confined in a system that is not going anywhere, is mass, not converted into mass, not equivalent to mass in some abstract accounting sense. It is mass. It resists acceleration. It bends space-time. It registers on a scale. Let me make that concrete, because this is the single most important idea in the entire video, and everything else is built on it. Imagine a sealed box with perfectly mirrored walls on the inside. You put it on a scale, and you write down the number. Now, without opening the box, you fill the interior with light. A great deal of light, bouncing endlessly between the mirrors, never absorbed, never escaping. The box is now heavier. Nothing was added that has any mass. A photon, a single particle of light, has no rest mass at all. It is one of the few things in the universe that is genuinely massless, which is exactly why it travels at the speed of light and cannot do anything else. You have added nothing but massless particles to the box, and the box weighs more than it did. The reason is that mass, properly understood, is not a property of the individual pieces. It is a property of the system. The mass of a system is the total energy contained inside it when the system as a whole is not moving. Your mirrored box is not going anywhere, but the light inside it is going everywhere, and all of that energy of motion is trapped. Trapped energy has nowhere to be except in the box's rest energy, and rest energy is mass. This is not a thought experiment with no consequences. A hot cup of coffee weighs measurably more than the same cup of coffee cold, not by much, something like 10 to the minus 14 kilograms for a typical mug, far below anything a kitchen scale could detect, but the number is calculable and the physics is not in doubt. A compressed spring weighs more than a relaxed one. A charged battery weighs more than a flat one. In every case, energy has been put into a system, the system is not moving as a whole, and the extra energy shows up as extra mass. There is a wrinkle in this that I want to give you now, because it will matter enormously later, and it is the sort of thing that makes people think they have misunderstood something when they have not. Sometimes binding energy makes a system heavier, and sometimes it makes it lighter, and the difference tells you something about the force doing the binding. Take an ordinary atomic nucleus. A helium nucleus contains 2 protons and 2 neutrons. Weigh those 4 particles separately, add up the numbers, and then weigh the assembled helium nucleus. The assembled nucleus is lighter than the sum of its parts. About 0.7% of the mass has gone missing. That missing mass is the binding energy, the energy that was released when the 4 particles fell together into a bound state, radiated away, and left the system lighter than it started. That deficit is precisely what powers a hydrogen bomb, and precisely what powers the sun. Fusion works because the products weigh less than the ingredients, and the difference leaves as energy. Now hold that thought, because when we get inside a proton, we are going to find the opposite. There, the bound system weighs far more than the sum of its parts, about 100 times more. The binding does not subtract mass. It creates almost all of it. That sign flip is not a contradiction. It is a fingerprint of a force behaving in a way that no other force behaves. And it is the reason the second half of this story exists at all. But we are not ready for it yet. Once you have that idea properly in your hands, a great deal of confusion evaporates. When I said at the start that 99% of your weight is not made of anything, that sounds like a paradox, only if you assume mass has to be built out of smaller pieces of mass, like a wall built out of bricks. It does not. Mass is built out of energy that cannot get away, and the interior of a proton, as we will see, is one of the most energetic environments in the universe. There is one more distinction to make, and it is going to come back at the end of the video in a way you will not expect. I have been describing mass as inertia, resistance to being pushed. But there is a second thing people call mass, and it is the property that makes an object respond to gravity. The mass in Newton's second law, force equals mass times acceleration, is inertial mass. The mass in his law of gravitation, the one that determines how strongly the Earth pulls on you, is gravitational mass. There is no obvious reason those two numbers should be the same. One describes how hard something is to shove. The other describes how strongly it is attracted. They are different properties of matter. They appear in different equations, and there is nothing in Newton's framework that requires them to match. They match anyway. They have been tested against each other for over 3 centuries, with increasing precision each time, and they have never once been caught disagreeing. Galileo is supposed to have dropped objects from a tower to make the point, though the story is probably apocryphal. Newton tested it with pendulums. In the 1880s and 90s, a Hungarian physicist named Lorand Ötvös built a torsion balance so sensitive that it could compare the two masses of different materials to about 1 part in 100 million, and found no difference. The most sensitive test we have was conducted from orbit and confirmed the two are identical to about 1 part in 1,000 million. That is not a small coincidence. It means that a lump of platinum and a lump of titanium, two substances with completely different internal compositions, different numbers of protons and neutrons, different proportions of binding energy fall at exactly the same rate. Whatever combination of energy and particles happens to make up an object's mass, gravity does not care about the recipe. It only cares about the total. Einstein took that coincidence seriously and built general relativity on it. But notice what that does and does not do. General relativity explains the consequences of inertial and gravitational mass being identical. It does not explain why mass exists in the first place. It takes mass as an input, exactly as Newton did, and tells you what space-time does in response. So here we are, with the two greatest theories in physics. Quantum field theory tells us what particles are and how they interact. General relativity tells us how mass curves space-time. And both of them, in their standard formulations, simply assume that mass is there. Which brings us to a problem that took physicists most of the 20th century to face properly. Because when you actually write down the equations of the Standard Model, carefully, in their most natural form, respecting the symmetries that make the whole structure work, you find that the theory does not merely fail to explain mass, it forbids it. Look in a mirror. The left side of your body is very nearly the right side reversed. Look at a flower, a snowflake, a starfish, a butterfly's wings. Nature is full of this, and we recognize it instantly, and we call it symmetry. The physicist's version of the word is broader and much more powerful. In physics, a symmetry is not about appearances. It is a statement that you can do something to a system and the laws governing it do not change. Here is the simplest example. Drop a ball in a laboratory in London and measure how it falls. Now carry the whole experiment to a laboratory in Lima and do it again. You get the same result. The laws of physics do not care where you are. That is called space translation symmetry, and it sounds so obvious that it feels like a waste of a name, until you realize that it is not logically required. There is no reason the universe had to work this way. It could have had preferred locations, places where gravity was slightly stronger for no reason. It does not. The rules are the same everywhere. Do the same with time. Run an experiment today, run it again in 100 years, and the laws are unchanged. That is time translation symmetry. Rotate your apparatus to face a different direction, and the laws do not change either. That is rotational symmetry. In 1918, a mathematician named Emmy Noether proved something about these symmetries that reorganized the whole of physics. She showed that every continuous symmetry of this kind is paired with a conserved quantity, something that cannot be created or destroyed. Time translation symmetry gives you conservation of energy. Space translation symmetry gives you conservation of momentum. Rotational symmetry gives you conservation of angular momentum. That is worth pausing on. Energy conservation is not a separate law of nature that happens to be true. It is a consequence of the fact that the laws do not change from one moment to the next. Symmetry is not a pretty feature of physics. It is the machinery underneath. And in the middle of the 20th century, physicists discovered that this machinery reached much further than anyone had suspected. That symmetry did not merely produce conservation laws, but produced the forces themselves. The kind of symmetry involved is more abstract than mirrors and rotations, and I want to explain it without the mathematics, because the idea is graspable and the payoff is enormous. Every particle in quantum theory is described by a field, and that field has a property at every point that behaves a little like a phase, or an angle on a dial. The absolute value of that angle is not physically meaningful. You can rotate every dial in the universe by the same amount, and nothing observable changes. That is a symmetry. So far, so harmless. Now demand something much stronger. Demand that you can rotate the dial by a different amount at every separate point in space, independently, and that the laws of physics still do not change. That demand breaks the equations immediately. Comparing a field at one point with the field at a neighboring point becomes meaningless when the dials have been twisted by different amounts. The only way to repair the damage is to introduce a new field, a field whose job is to keep track of the twisting, to connect one point to the next, to tell you how much to compensate. That compensating field is a force. This is called the gauge principle, and it is the most productive idea in modern physics. Demand this kind of local symmetry with the simplest possible dial, a single circular phase, a structure mathematicians call U1, and out falls electromagnetism, with the photon as its carrier. Demand it for a slightly richer structure, called SU2, and out falls the weak nuclear force, with the W and Z bosons carrying it. Demand it for a structure called SU3, which has three internal states physicists whimsically named colors, and out falls the strong nuclear force, with 8 gluons. 3 of the 4 fundamental forces are not separate discoveries bolted onto the theory. They are what you get when you insist on symmetry and then follow the mathematics. The universe's forces appear to be the price of a symmetry being local rather than global. Gravity, notably, is not in this list. It has no accepted quantum description. It does not arise from a gauge symmetry in the same way, and its absence from this structure is going to matter before the night is out. Now here is where the beauty turns into a disaster. The gauge principle, taken at face value, requires every one of those force-carrying particles to be exactly massless. You can see why in outline. A mass term in the equations is a specific mathematical object, and when you perform the local twisting that the symmetry demands, that mass term does not survive intact. It changes, and if it changes, the symmetry is broken, and if the symmetry is broken, the entire scaffolding that generated the force in the first place collapses. Worse, the calculations stop working. Quantities that should be finite come out infinite. The theory ceases to predict anything. For the photon, this is fine. The photon is massless as far as anyone can measure. The experimental upper bound on its mass is around 10 to the minus 18 electron volts, which is a way of saying that if it has any mass at all, it is unimaginably small. That is why electromagnetism has unlimited range. It is why you can see a galaxy whose light left before the Earth existed. It is why radio works. For the weak force, it is a catastrophe. The W boson has a mass of about 80.377 giga-electron volts. The Z boson comes in at 91.1876 giga-electron volts. To put those numbers in a form you can hold on to, each of them weighs roughly 90 times as much as a proton. These are among the heaviest particles ever produced in a laboratory. They are not slightly massive, they are enormously massive, and the theory that predicts their existence insists they weigh nothing. We know they are heavy, not just because we have measured them directly, which we have, at CERN, since 1983, but because the weak force behaves in a way that only heavy carriers can produce. The weak nuclear force has a range of about 10 to the minus 18 meters. A proton is roughly 1.7 times 10 to the minus 15 meters across. So the weak force reaches about 1/1000th of the way across a proton, and then, effectively, stops. That short range is a direct consequence of mass. Heavy force carriers cannot travel far. Massless ones travel forever. If the W and Z were massless, as the equations demand, the weak force would behave like electromagnetism. Infinite reach, everywhere, all the time. Think about what that would mean. The weak force is what turns one type of quark into another. It is what makes radioactive decay possible. It is the bottleneck in the first step of the reaction that powers the sun, the step that makes stellar burning slow enough to last billions of years instead of exploding in an instant. A weak force with unlimited range would not be weak. It would be a fourth long-range force acting on everything, and every structure built by the other three would have to survive it. The universe would not look remotely like this one. And the problem does not stop with the force carriers. It comes for you directly. The matter particles, quarks and leptons, the things you are actually built out of, come in two varieties that physicists call left-handed and right-handed. The distinction is a quantum property called chirality, and you can loosely picture it as whether the particle's intrinsic spin points along its direction of motion or against it, though that picture leaks if you press it. Here is the crucial fact. The weak force acts only on the left-handed ones. It ignores right-handed particles completely. This is not a small asymmetry. It is total, and it was one of the great shocks of the 1950s when it was discovered that nature distinguishes left from right at the most fundamental level. As far as anyone has ever been able to detect, right-handed neutrinos do not even exist. Now, a mass term for a matter particle is, mathematically, a bridge between its left-handed and right-handed components. Mass is what converts one into the other, continuously. But if the left-handed version carries a weak charge and the right-handed version does not, then that bridge connects two things that the symmetry treats completely differently, and the bridge is not gauge invariant. Writing an electron mass into the equations by hand destroys the theory in exactly the same way that writing a W mass does. So the Standard Model, in its natural and undistorted form, demands massless force carriers and massless matter. Every particle in it must travel at the speed of light. Nothing can slow down, nothing can be caught, nothing can form a bound state. No electron can ever settle into orbit around a nucleus. No atom can exist. No chemistry can happen. No star can form. And there is nobody in that universe to notice how elegant the equations are. Wolfgang Pauli saw this problem the first time the framework was presented. In 1954, Chen-Ning Yang gave a seminar at Princeton on the general theory of these gauge fields, work he had done with Robert Mills. Pauli, sitting in the audience, interrupted almost immediately to ask what the mass of the new fields was. Yang did not have an answer. Pauli pressed. Yang, by his own later account, was so unsettled that he sat down and stopped speaking. Robert Oppenheimer had to encourage him to continue. The mass problem was recognized as fatal at the very first presentation of the idea, and it stayed fatal for a decade. I want to flag something here that will come back at the end, because this is the moment it first becomes visible. Notice what kind of problem this is. Nobody was asking why mass exists in some philosophical sense. They were asking a technical question. How do you write a theory that has both the symmetry and the mass? Physics is very good at how, and almost silent on why. Keep that sentence somewhere. We will need it later, when the how has been answered twice over, and the why is still standing there untouched. The solution, when it came, did not remove the symmetry. That was the trick. The symmetry was too valuable to give up. Without it, there is no force, no renormalizability, no theory at all. Instead, somebody had the idea of keeping the symmetry in the laws and breaking it somewhere else entirely. The answer arrived from a place nobody in particle physics was looking, which was the study of very cold metal. In the 1950s, physicists were working out how superconductivity happens, why certain materials, cooled far enough, conduct electricity with no resistance whatsoever. The full theory arrived in 1957, and it contained a detail that at the time seemed like a curiosity confined to laboratory metals. Inside a superconductor, the photon behaves as though it has mass. This is not a metaphor. In empty space, an electromagnetic field extends indefinitely, weakening with distance but never stopping, because the photon is massless. Inside a superconductor, a magnetic field pushed in from outside dies away exponentially over a very short distance and cannot penetrate the bulk of the material at all. That expulsion is called the Meissner effect, and it is why a magnet floats above a cooled superconductor in every demonstration you have ever seen. The reason the field cannot get in is that the superconducting state is not empty. It is filled with a condensate of paired electrons, and the photon moving through that condensate acquires an effective mass. The mass is not intrinsic to the photon. It is a property the photon takes on because of the state it is moving through. Philip Anderson, a condensed matter physicist, spelled out in 1962 and 63 what this implied. If a medium could give a photon mass, then a suitably strange medium, a medium that filled all of space, could give any gauge boson mass, without touching the underlying symmetry of the equations. The symmetry would still be there. It would simply not be respected by the state of the world. Around the same time, working from a different direction, Yoichiro Nambu was formalizing the general idea. His term for it was spontaneous symmetry breaking, and the word spontaneous is doing important work. It means the breaking is not imposed from outside. Nobody adds a term to the equations. The equations stay symmetric, and the lowest energy configuration they permit simply fails to be. Nambu received the Nobel Prize for this in 2008, 47 years after the work. Jeffrey Goldstone worked out a crucial consequence in 1961, which we will get to shortly, because it initially looked like it killed the whole idea. There is an irony buried in Nambu's involvement that is worth noticing now, because it will pay off later tonight. Nambu did not develop spontaneous symmetry breaking in order to explain the masses of force carriers. He developed it, working with Giovanni Jonah Lasigno in 1961, to explain the mass of the proton and the neutron. He had noticed that the superconducting condensate, a medium that fills a region and changes the properties of things moving through it, looked like a good model for whatever was going on inside nuclear matter, and he suspected that the mass of a nucleon might arise from a symmetry being broken by the vacuum rather than being an intrinsic property. He was right, and his idea turned out to apply in two entirely separate places. One of them gives mass to the electron and the W boson. The other gives mass to U. At the time, nobody could distinguish the two applications clearly, and it would be another decade before the theory of the strong force existed in a form that could sort them out. Hold on to that. We are going to come back to it in a way that changes the whole picture. Let me give you the picture that every physicist carries in their head for this, because once you have it, you will never lose it. Picture a shape like a sombrero, or the bottom of a wine bottle. There is a hump in the middle, rising to a peak, and around that hump there is a circular valley, a brim, a trough, a ring of lowest points, all at the same height. Physicists call this the Mexican hat potential. The height of the surface at any point represents energy. Balls roll downhill toward lower energy, as balls do. Now here is the question that matters. If I hand you a ball and ask you to place it on this shape so that the symmetry is perfectly preserved, where do you put it? You have exactly one choice. You put it on the peak, dead center. Only there is the arrangement perfectly symmetric. Spin the hat around its axis, and nothing about the picture changes. Every other position singles out a direction, but the peak is the highest point on the surface. A ball balanced there is in an unstable equilibrium, the way a pencil balanced on its tip is unstable. The tiniest disturbance, and in quantum mechanics there is always a disturbance, because nothing can be perfectly still, and the ball rolls off, down the slope, and comes to rest somewhere in the circular valley. The ball cannot stay in the middle. The moment it settles in the trough, the symmetry is gone, not from the hat. The hat is exactly as symmetric as it always was. From the situation, there is now a direction that is special, the direction the ball happens to have rolled. Ask which way is which, and the answer is no longer all directions are equivalent. One of them has the ball in it. That is spontaneous symmetry breaking in a single image. The law, the shape of the hat, remains perfectly symmetric. The state, where the ball actually is, does not, and nothing chose the direction. There was no reason for the ball to go one way rather than another. It simply had to go somewhere, because staying in the middle was not an option. Now, Goldstone's 1961 result. When a continuous symmetry breaks this way, you always get a leftover, a new particle with exactly zero mass, corresponding to the fact that the ball can roll freely around the circular trough without any energy cost at all. Rolling around the brim is free, climbing up the sides is not. That free direction shows up in the theory as a massless particle, and it is called a Goldstone boson. This looked like a fatal problem. The whole point of the exercise was to get rid of unwanted massless particles. Now the cure was producing new ones that had never been observed. The resolution is the piece of the story that is genuinely beautiful, and it is what the 1964 papers are about. When the broken symmetry is a gauge symmetry, the local kind that generates forces, the massless Goldstone boson does not appear as a separate particle at all. It gets absorbed by the gauge boson. Physicists say, with a certain relish, that the gauge boson eats it. And when it does, it gains exactly what it needs. A massless particle, like a photon, has two possible polarizations, two ways of oscillating perpendicular to its direction of travel. A massive particle has three. It can also oscillate along its direction of motion, because unlike a massless particle, it does not have to travel at the speed of light. That third polarization has to come from somewhere. It comes from the swallowed Goldstone boson. The unwanted massless particle is precisely the missing degree of freedom that a massive force carrier requires. Nothing is lost. The bookkeeping is exact. A massless gauge boson plus a massless Goldstone boson equals one massive gauge boson, and the symmetry of the underlying equations is never violated. In 1964, 3 separate groups published this within 4 months of each other. Robert Brout and François Englert, working in Brussels, got there first. Their paper appeared in Physical Review Letters in August. Peter Higgs, working alone in Edinburgh, submitted his in the summer, and it was published in October. Gerald Guralnick, Carl Richard Hagen, and Tom Kibble published a third independent treatment in November. And here is the detail that decided whose name would end up on the particle. Higgs's paper was rejected. He had sent it to a journal called Physics Letters, which was published at CERN, and the editor turned it down. The reason given was that the work was, in the phrase Higgs recounted for the rest of his life, of no obvious relevance to physics. He was 35 years old. He had just written down one of the most consequential ideas of the century and been told it was irrelevant. So he revised it. He added a paragraph, a short one, near the end, pointing out that the mechanism did not only give mass to the force carriers. The field doing the work would itself have an excitation, a ripple, and that ripple would be a new particle, a massive scalar boson, something you could, in principle, go out and find. Then he sent the revised paper to Physical Review Letters in the United States, and they published it on the 19th of October, 1964. That added paragraph is the entire reason the particle is called the Higgs boson. Brout and Englert had the mechanism. All 3 groups had the mechanism. Higgs was the one who wrote down, explicitly, that the mechanism predicted a findable thing. It took 48 years to find it. Higgs was 83 when it turned up. The reaction to all 3 papers, at the time, was close to silence. For most of the rest of the decade, the work was largely ignored. Steven Weinberg used the mechanism, in 1967, to construct a unified theory of the electromagnetic and weak forces in a paper called A Model of Leptons, that is now one of the most cited papers in the history of the field. In the first 4 years after publication, it was cited almost not at all. The reason nobody paid attention was technical. It was not clear that a theory with spontaneously broken gauge symmetry could actually be calculated with whether it would produce finite, sensible answers or dissolve into infinities like every previous attempt. Without that guarantee, the whole construction was an elegant guess. The guarantee arrived in 1971 and 72 from a Dutch graduate student named Gerard Hooft and his supervisor, Martinus Veltman. They proved that these theories are renormalizable, that you can extract finite predictions from them. Weinberg later described the effect on the field as immediate. The citation count of his ignored paper went from a trickle to a flood. Hooft and Veltman received the Nobel Prize in 1999. Glashow, Salem, and Weinberg had received theirs for the electroweak unification 20 years earlier, in 1979. So by the mid-1970s, the mechanism was established theory, and the W and Z bosons were found at CERN in 1983, exactly where the theory said they should be, and Carlo Rubbia and Simon van der Meer had a Nobel Prize the following year for finding them. Everything fit, everything worked, and there was still one object in the whole structure that nobody had ever seen, the field itself, and the ripple in it that Higgs had described in his rejected, then revised paragraph. Which raises the obvious question, and it is the one that determines everything that follows. If there really is a field filling all of space, and it is the reason particles have mass, then what exactly is it doing right now, in this room, in the space between your ribs, in the emptiest place in the universe? Every particle you have ever heard of is a ripple in a field. That is the central claim of quantum field theory, and it is easy to say and hard to feel. There is an electron field spread through all of space, and an electron is a localized excitation in it, a wave packet, a disturbance, a place where the field is doing something. There is a photon field, and light is a ripple in that. There is a quark field, and so on. The particles are not little objects moving through empty space. They are behaviors of fields that are already everywhere. Now, all of these fields are restless. Even in what we call a vacuum, they are not still. Quantum mechanics forbids perfect stillness. The uncertainty principle guarantees that a field can never simultaneously have a definite value and a definite rate of change, so it fluctuates. Particle-antiparticle pairs flicker into existence, borrow energy from nothing at all, and annihilate before the universe can notice the debt. This is happening constantly, everywhere, right now, in the space between your fingers. But when you average it all out, when you ask what the field's value actually is, over time, in empty space, every one of these fields gives the same answer: 0. The fluctuations cancel. The borrowing balances the repaying. The universe registers empty space as containing, on average, nothing. Every field except one. The Higgs field, alone among the fields we know of, has a lowest energy state that is not 0. Its average value in empty space, in the emptiest place you could find in the universe, is 246 giga-electron volts. To get some grip on how large that is, the entire rest energy of a proton, the whole thing, all 938 mega-electron volts of it, is a little under 1 giga-electron volt. So the standing value of the Higgs field in empty space corresponds to about 260 times the rest energy of a proton, present in every location, always, as the baseline, not as a fluctuation, as the floor. That is the Mexican hat, made real. The center of the hat, the symmetric point where the field's value is 0, is the unstable peak. The circular trough is where the field actually sits. It rolled off the hump and settled in the brim, and it has been there ever since. Take a moment with this one, because I think it is the strangest fact in the whole of physics, and it goes past most people unexamined. Right now, in the room where you are lying, there is a field. It is not made of particles. It is not moving. It is not doing anything you could detect with any instrument you own. And it is not 0. Look at the space between your ribs as you breathe in, the gap between one bone and the next, the volume your lungs are filling. It is not empty, it has a value. 246 giga-electron volts of standing field, in that gap, and in the gap beside it, and in every gap everywhere out to the edge of the observable universe. Go to the emptiest place anyone has ever found, the great voids between galaxy clusters, where a cubic meter might contain a single atom, and the nearest star is tens of millions of light years away. The field is there too, at exactly the same value. It does not thin out. It does not fall off with distance. It is not a substance filling a container. It is a number that the universe holds, uniformly, everywhere at once, and it has held it since the universe was about 100 billionth of a second old. And now the part that actually matters, because a field being non-zero is only interesting if it does something. Here is what it does. Remember from earlier that matter particles come in left-handed and right-handed versions, and that a mass term is a bridge between them. In a universe where the Higgs field's value was zero, that bridge could not be built. The symmetry would forbid it, and every particle would be locked into a single chirality and would travel at the speed of light forever. But the field is not zero, and its non-zero value provides exactly the missing piece. An electron moving through space is continuously interacting with the standing Higgs field, and each interaction flips it, left-handed to right-handed, right-handed to left-handed, over and over, at a rate that depends on how strongly that particular kind of particle couples to the field. A particle that keeps flipping between chiralities cannot travel at the speed of light. It is not, at any moment, purely one thing moving purely one way. The flipping slows it, in the specific sense that it now has a rest frame, a frame in which it is standing still, which no massless particle has. Mass, in this reading, is the rate of that flipping. To be massive is to be unable to keep going straight. Some particles do not couple to the field at all. The photon is one of them. It has no Yukawa coupling, it never flips, and so it remains exactly massless and travels at the speed of light and always will. That is not an accident of the theory. It is the reason light behaves the way it does. The reason electromagnetism has infinite reach. The reason the night sky contains anything at all. The same field that slows everything else down leaves light entirely alone. There is another consequence of all this that I find harder to shake than the field itself, and it concerns time. The Higgs field has not always been sitting in the trough. At very high temperatures, the shape of the potential is different. The hump in the middle of the hat flattens out, and the lowest energy point moves back to the center. Heat the universe enough, and the ball is not in the brim. It is in the middle, where the symmetry is unbroken, and the field's value is zero. That was the state of the universe once. In the first instance after the Big Bang, when the temperature corresponded to energies above roughly 160 giga-electron volts, the Higgs field's average value was zero, and every fundamental particle in existence was massless. Nothing had a rest frame. Nothing could be caught. Everything moved at the speed of light, in every direction, forever, and no structure of any kind was possible. Then the universe expanded and cooled. The shape of the potential changed underneath the field. The center stopped being the lowest point, and the field slid into the trough. Mass switched on. Lattice calculations indicate this was a smooth crossover rather than an abrupt phase transition, so there was no sharp moment, no boiling, no bubbles of the new phase colliding, just a gradual settling. It happened about 10 to the minus 11 seconds after the beginning. 100 billionth of a second. Before that instant, in the entire history of the universe, nothing weighed anything. I want to correct the analogy you have almost certainly heard, because it is misleading in a way that matters. The popular version says the Higgs field is like molasses or treacle, and particles get mass by dragging through it. Heavy particles interact more, so they are more slowed. That picture fails at the first test. Drag slows things down continuously. If you push an object through treacle and let go, it stops. But a particle moving through the Higgs field at constant velocity keeps that velocity indefinitely, forever, with no loss. The Higgs field does not oppose motion. It does not steal energy. An electron drifting through intergalactic space is not gradually being brought to rest by the Higgs field, and if it were, Newton's first law would be false and physics would have noticed. The field does not resist motion. It resists motion at the speed of light. That is a different statement, and it is the correct one. There is one more piece of the mechanism to name, and it is the one that will come back to haunt us in about half an hour. How strongly a given particle couples to the Higgs field is described by a number called a Yukawa coupling, and every particle has its own. Multiply the field's standing value of 246 giga-electron-volts by a particle's Yukawa coupling, divide by the square root of 2, and you get that particle's mass. That is the whole formula. It works perfectly. The top quark's coupling is very close to 1. The electrons is about 3 parts in a million. Where do those numbers come from? They come from measurement. Somebody measured the mass of the electron, divided by the field value, and wrote down the coupling. The theory does not predict them, constrain them, relate them to each other, or explain them in any way whatsoever. They are inputs. Hold that thought too. We now have 2 things parked: the strange coincidence about Nambu's original target, and the fact that every mass in the standard model is a number typed in by hand. And there is a third thing I should be honest about while we are here, which is that the hat itself is an assumption. Nobody has ever measured the shape of the Higgs potential. The Mexican hat is the simplest shape that does the job. It produces spontaneous symmetry breaking. It gives the right particle content. It works. But the property that would actually confirm the shape is how strongly the Higgs field interacts with itself. And that self-interaction is the least measured thing about the entire sector. Measuring it means producing 2 Higgs bosons in the same collision and watching how often that happens. And it is rare enough that the current combined limits from both LHC experiments only tell us the rate is somewhere below about 2.5 times what the standard model predicts. So the picture I have just spent 20 minutes drawing for you rests on a potential whose shape is inferred rather than observed. It is very probably right. It is not confirmed. Because before we can deal with either, there is a much more immediate question. All of this, the hat, the ball, the standing field, the flipping, is a story. An elegant story, internally consistent, capable of producing the right numbers when the right inputs are supplied. But it describes something invisible that does nothing detectable and cannot be switched off. How on earth do you check whether it is true? You cannot measure the Higgs field directly. It is the same everywhere, always, and you cannot turn it off, and there is nowhere to stand outside it and compare. But if the field exists, then like every field, it must have ripples. Shake it hard enough, and you should get a particle. An excitation in the Higgs field itself, a massive scalar boson with no spin and no electric charge. That was the content of the paragraph Peter Higgs added to his rejected paper. Shaking a field hard enough means concentrating an enormous amount of energy into a very small volume, and there is only one way we know to do that. Take 2 protons, accelerate them to very near the speed of light in opposite directions, and let them hit each other head-on. The machine built to do it is the Large Hadron Collider, a ring 27 kilometers around, buried about 100 meters beneath the border between France and Switzerland, cooled with liquid helium to under 2 Kelvin, colder than the empty space between stars. It began operating in 2008, broke almost immediately, was repaired, and started producing physics in 2010. The difficulty is not producing Higgs bosons, it is noticing them. Roughly 1 collision in a billion makes one, and when it is made, it does not last. The Higgs boson's lifetime is about 1.6 times 10 to the minus 22 seconds. Nothing has ever observed a Higgs boson. Everything we know about it has been reconstructed from the debris it leaves behind. It is worse than that, because most Higgs bosons decay in ways that are impossible to distinguish from ordinary collision debris. The most common decay produces a pair of bottom quarks, and the collider produces bottom quarks constantly, by the million, through completely mundane strong force processes. Looking for Higgs bosons that way is like listening for a specific whisper in a stadium. So the search concentrated on two rare but clean channels. The first is decay into two photons, a route taken by only about 0.2% of Higgs bosons. But photons are measured with beautiful precision, and the background beneath them is a smooth, predictable curve, so a bump stands out. The second is decay into two Z bosons, which then each decay into a pair of leptons, giving 4 charged particles that can be tracked and whose combined energy can be added up. That channel is even rarer and even cleaner. There is one further constraint that people rarely hear about. The collider produces collisions far faster than any storage system on Earth could record them. Hundreds of millions per second. The detectors cannot keep them. A system called the trigger looks at each event in real time, in a fraction of a millionth of a second, and decides whether to save it or throw it away, and the overwhelming majority are thrown away permanently. If the trigger had been configured to discard the signatures a Higgs boson leaves, the particle would have been produced tens of thousands of times, and nobody would ever have known. The discovery depended on deciding in advance what to keep. 2 detectors, Atlas and CMS, watched for that debris. They were built by separate collaborations of thousands of physicists each, using different technologies and different analysis strategies, and, this is the part that matters, they were kept deliberately blind to each other's results. If both of them saw the same thing independently, it would be very difficult to argue the thing was not there. By the middle of 2012, both had been seeing a small bump for months. The seminar was announced for the morning of the 4th of July, 2012, in the main auditorium at CERN. Word had got around. Students queued through the night, in the corridor outside, sleeping on the floor, to get seats in a room that holds a few hundred people. The auditorium is full. Peter Higgs is in the audience. He is 83 years old, and he wrote the paper that predicted this in 1964, and he has flown down from Edinburgh because somebody from CERN telephoned and told him he ought to be there. The CMS spokesperson presents first. There is a plot on the screen, a smooth falling curve of expected background, and the data points sitting on top of it, and near 125 giga-electron volts, the points climb away from the curve. Then the significance number appears. 5 standard deviations. In this field, 5 sigma is the threshold for saying you have found something. A false alarm probability of about 1 in 3.5 million. The Atlas spokesperson presents second, with a different detector, a different collaboration, a different analysis. The bump is in the same place. The significance is the same. The room applauds for a long time. The cameras find Higgs in his seat. He has taken off his glasses and is wiping his eyes. Afterwards, asked how it felt, he said something almost aggressively understated, that it was very nice to be right, occasionally. The Nobel Prize followed in 2013, awarded to François Englert and Peter Higgs. Higgs, who did not own a mobile telephone, missed the announcement entirely. He had gone out to lunch to avoid the press, and found out on the way home when a former neighbour stopped him in the street to congratulate him. Robert Brout, who had published the mechanism with Englert in August of 1964, several weeks before Higgs, had died in May of 2011. He missed the discovery by 14 months, and the prize by 2.5 years. The Nobel is not awarded posthumously. Guralnick, Hagen, and Kibble, who published the third independent version that November, were not included either, because the prize cannot be split more than 3 ways. So the story has a clean ending. 48 years from a rejected manuscript to a confirmed particle. A prediction made about a field nobody could see, verified by two independent instruments on the same morning. The mass of the boson has since been pinned down to about 125.11 giga-electron volts, with an uncertainty of around a tenth of a giga-electron volt, a precision of roughly 0.09%. I want to be clear that I am not about to take any of that away. It is one of the finest things our species has done. But I do want to deal with the phrase, because it has done real damage. Somewhere in the coverage, the Higgs boson became the God particle. That name comes from a 1993 popular book by the physicist Leon Lederman. Lederman has said the title was not his choice, that his preferred title was a mild profanity, expressing how maddeningly difficult the thing was to find, and the publisher refused it. The replacement stuck, and it has been repeated ever since by people who never read the book. Peter Higgs disliked the name and said so repeatedly, for two reasons. He thought it might give unnecessary offense to religious people, and he thought it was simply wrong. The particle does not create matter, it does not create the universe, it has no special connection to anything divine. While we are clearing away debris, there is a second thing worth dealing with in one paragraph, because it circulated widely before the machine switched on, and it resurfaces with every restart. The claim was that colliding protons at these energies might produce a black hole, or tear something, or open something that should stay closed. The answer is simple, and it does not require trusting anyone. Cosmic rays, particles accelerated by processes out in the galaxy, strike the Earth's upper atmosphere continuously, and some of them arrive with energies far beyond anything the collider produces. They have been doing this for 4.5 billion years, without pause, over the whole surface of the planet. The moon has absorbed the same bombardment with no atmosphere to soften it, and it is still there. Every star and every planet in the solar system has run this experiment, at higher energies, for longer, more times than any machine ever will. If those collisions produced anything dangerous and stable, none of this would be here to worry about it. And here is the deeper problem with the coverage, the one that is not about the nickname at all, and it is the reason for everything in the second half of tonight. The story the world was told on the 4th of July 2012 was, scientists have discovered the particle that gives everything mass. The first half of that sentence is true, the second half is not. The Higgs mechanism gives mass to fundamental particles, the electron, the individual quarks, the W and Z bosons, the things that have no internal structure. That is a real and important achievement, and without it, there would be no atoms. But you are not made of fundamental particles in any way that dominates your weight. You are made of atoms. Atoms are almost entirely nucleus, and the nucleus is protons and neutrons, and protons and neutrons are not fundamental. They are composites, built out of quarks, held together by the strong force. So let us do what nobody did on the 4th of July 2012, in front of those cameras. Let us take the thing the Higgs mechanism explains, apply it to an actual proton, and see how much of the proton it accounts for. The arithmetic takes about 20 seconds, and it is the moment this entire subject stops being a triumph and starts being a mystery. Let us stop for a moment and put the pieces we have on the table, because we are at the hinge of the night, and I want you carrying everything you need. We started with a number on a scale, and the claim that almost none of it is made of anything. We took the word mass apart, and found that it does not mean quantity of stuff. It means resistance to being pushed, and by Einstein's reading, it is nothing more or less than the total rest energy of a system. A box of light weighs more than an empty one. Energy that cannot get away is mass. Then we looked at the theory that describes the particles you are built from, and found that in its natural form, it forbids mass entirely, because the symmetry that generates the forces cannot tolerate a mass term. A universe obeying those equations as written has nothing in it but massless things moving at the speed of light forever. Then we watched physicists solve that, by keeping the symmetry in the laws and breaking it in the state of the world. A field that is not zero in empty space. A ball that could not stay in the middle of the hat. 246 giga-electron-volts standing everywhere, flipping particles between chiralities, giving them rest frames and therefore mass. Predicted in 1964, confirmed in 2012, precise to 0.09%. Now let us apply it. A proton is not a fundamental particle. It is a composite, and its recipe is simple enough to state in one line: 2 up quarks and 1 down quark, held together by the strong nuclear force. Those quarks are fundamental. They get their masses exactly the way the Higgs mechanism says they should. A Yukawa coupling times the standing field value, everything working as advertised. And because they are fundamental particles whose masses have been measured, we can look them up. The current value for the up quark's mass is about 2.16 mega-electron-volts. The down quark comes in at about 4.67, so a proton contains 2 up quarks at 2.16 each, and 1 down quark at 4.67. 2.16 plus 2.16 plus 4.67. That is about 9 mega-electron-volts. The measured mass of a proton is 938.272 mega-electron-volts. I would like to let that sit for a second. 9 against 938. The 3 quarks, the actual constituents, the things the proton is made of, every one of them given its mass by the field that took half a century and one of the largest machines ever built to confirm, account for slightly under 1% of the proton's mass. 99% of the proton is unaccounted for. And a proton is not a special case. A neutron does the same thing. 2 down quarks and an up, summing to about 9 mega-electron-volts of quark, against a measured mass of 939.565. Every proton and every neutron in the universe does this. Now count what you are. Your body is atoms. Each atom is a cloud of electrons around a nucleus, and although the electron cloud is what gives an atom its size and does all of its chemistry, it contributes almost nothing to the weight. An electron is about 1/1836th the mass of a proton. Essentially, all of an atom's mass is in the nucleus, and the nucleus is nothing but protons and neutrons. So if 99% of a proton's mass is not its quarks, then 99% of a nucleus is not its quarks, and 99% of an atom is not its quarks, and 99% of you is not made of anything the Higgs mechanism explains. Take an 80-kilogram person. Roughly 800 grams of that traces back to the Higgs field. 79 kilograms of it does not. That is what I meant at the start, when I said that almost none of your weight is made of anything, and now you can see it is not a figure of speech. It is a subtraction. Before we go further, I want to defend the Higgs field for a paragraph, because it only accounts for 1%, can easily curdle into "it does not matter," and that would be badly wrong. That 1% is load-bearing. The electron's mass comes entirely from the Higgs field, and an electron with no mass would travel at the speed of light and could never be captured into orbit around a nucleus. No atoms. The W and Z bosons get their masses from the Higgs field, and without those masses, the weak force would have unlimited range, and stellar physics would be unrecognizable. The tiny difference between the up quark's mass and the down quark's mass, a couple of mega-electron volts, both of them Higgs-derived, is what decides which way certain nuclear reactions run. In fact, that last one deserves a sentence of its own, because it is one of the finest examples in physics of a small number doing enormous work. The neutron is slightly heavier than the proton, 939.565 against 938.272. a difference of about 1.3 mega-electron-volts, roughly 1 part in 700. That tiny gap is the reason a free neutron decays in about 15 minutes, while a free proton appears to be stable forever, and it is therefore the reason hydrogen exists as the most common substance in the universe. And it is the outcome of a competition. Electromagnetic energy pushes one way, the proton carries charge, and the neutron does not, and that charge energy should make the proton the heavier one. The quark masses push the other way, because the neutron's recipe swaps an up quark for a heavier down quark. The quark mass term wins, by a hair. If it lost, if the proton were the heavier one, then hydrogen atoms would decay, there would be no water, no organic chemistry, and no listeners. So the difference between a universe with chemistry and a universe without it comes down to a couple of mega-electron volts of Higgs-derived quark mass beating a couple of mega-electron volts of electrical energy. The 1% is small. It is not unimportant. The pion makes the point even more sharply, and I bring it in because it becomes important later. A charged pion is the simplest thing the strong force builds. One quark and one antiquark, bound together. Add up the quark masses inside it, and you get around 7 mega-electron volts. The measured mass of a charged pion is 139.57 mega-electron volts. 7 in, 140 out, a factor of 20. And unlike the proton, where you might tell yourself a story about 3 particles jostling, this is 2 objects, bound, weighing 20 times what they weigh apart. Something is generating mass inside these composites, on an enormous scale, and it is not the Higgs field. Now, before we go and find out what it is, I want to be precise about a thing, because I do not want to overstate the case, and there is a subtlety here that matters. When physicists do the full accounting on the proton, and I will show you that accounting shortly, the piece attributable to the Higgs field is not quite 1%. It comes out closer to 9%. The difference is that a proton is not only its 3 valence quarks. Its interior is churning with quark-antiquark pairs appearing and vanishing, including strange quarks, which are considerably heavier than up and down quarks, and those transient heavy quarks carry Higgs-derived mass too. So the honest number depends on the question. If you ask what fraction of the proton's mass comes from the 3 quarks in the recipe, it is about 1%. If you ask what fraction traces back to the Higgs mechanism in total, including everything fluctuating inside, it is somewhere around 9%. Either way, the conclusion is identical, and either way, the popular story is wrong. Even taking the most generous accounting, more than 90% of the mass of ordinary matter has nothing to do with the Higgs field. Which means the discovery that dominated the science news of 2012, the confirmation of a field that everyone was told gives everything its mass, accounts for under 1/10 of the mass of everything you have ever touched. I want to be careful about how I say the next part, because it is easy to turn it into an accusation, and it does not deserve to be one. Nobody lied. The physicists at that seminar knew exactly what the Higgs mechanism does and does not explain, and they have never claimed otherwise in a paper or a lecture. The problem is that the field that gives fundamental particles their rest mass is a sentence with a clause in it, and the field that gives everything mass is not, and the second one travels much better. Over 13 years of repetition, the clause fell off. It is the most consequential piece of misinformation in physics, and it was produced by simplification rather than by anyone's intent. So where does the rest of you come from? The answer involves the strongest force in nature, a particle that pulls on itself, and a symmetry that breaks in an entirely different way from the one we have spent the last hour on. It produces 100 times more mass than the Higgs field does. It was worked out separately, and almost nobody has heard of it. The strong nuclear force is called that because it is the strongest force we know of. and it is worth understanding why it had to be. An atomic nucleus contains protons, and protons are positively charged, and positive charges repel each other with enormous vigor at short range. Two protons a femtometer apart push each other apart with a force you could feel if you could somehow hold them. Left alone, a nucleus would fly to pieces instantly. Something holds it together, and whatever it is, it has to beat electromagnetism at close quarters by a wide margin. That something is the strong force, and it comes out of the gauge principle exactly as electromagnetism and the weak force do, from a symmetry structure called SU3, whose three internal states physicists decided to call colors, purely as a naming convention. Nothing about this has anything to do with visible color. Quarks carry color charge the way they carry electric charge, and the force between them is carried by particles called gluons. There are 8 gluons, and like the photon, they are massless. But there is a structural difference between gluons and photons that is the single most consequential fact in this half of the story, and it is easy to state. The photon carries the electromagnetic force, but has no electric charge of its own. Two photons crossing paths ignore each other completely. Light passes through light without interacting. Gluons carry the strong force and do have color charge of their own. Gluons pull on gluons. That one difference changes everything about how the force behaves, and it produces two properties that have no parallel anywhere else in physics. It is also worth knowing that the force holding a nucleus together is not this force directly. Protons and neutrons are color neutral overall. The colors inside them cancel, the way an atom is electrically neutral overall, even though it is built from charges. What binds one proton to the next is a leftover, a residue of the strong force leaking past the cancellation, in the same way that electrically neutral atoms still attract each other weakly enough to form liquids. The force that binds the nucleus is the crumbs. The force operating inside a single proton is the whole loaf, and it is roughly 100 times stronger. The first is asymptotic freedom. When two quarks are extremely close together, the strong force between them is weak, so weak that at very short distances, quarks behave almost as if they were free particles, barely aware of each other. This is the opposite of every force you have intuition for. Gravity and electromagnetism get stronger as things get closer. The strong force gets weaker. David Gross, Frank Wilczek, and independently David Politzer worked this out in 1973, and it earned them the Nobel Prize in 2004. The second property is what happens when you go the other way. Pull two quarks apart, and the force between them does not weaken with distance, it stays roughly constant, or grows. The field between them does not spread out and thin the way an electric field does, fanning out in all directions and dropping off with the square of the distance. Because gluons attract each other, the field collapses into a narrow tube, a flux tube, a string of field running directly from one quark to the other, with the gluons holding themselves together instead of dispersing. Pulling on that tube is like pulling on a length of elastic. The further you stretch it, the more energy you are putting in, and unlike elastic, it does not thin out, and it does not snap from fatigue. What happens if you keep pulling? You put more and more energy into the tube, until at some point there is enough energy stored in it to create a new quark and antiquark from nothing at all. And that is exactly what happens. The tube breaks, and a fresh quark-antiquark pair appears at the break, one attaching to each end. You pulled on a quark, hoping to extract it, and instead of getting a free quark, you got two bound systems where you had one. This is called confinement. You cannot get a quark out, not because we lack a strong enough machine, because the attempt itself manufactures new particles rather than yielding a free one. No isolated quark has ever been observed, and the theory says none ever will be. Now put those two facts together and look at what the inside of a proton must be like. Shrink yourself down. A proton is about 10 to the minus 15 meters across. You would need to line up 10 million of them to cross the width of a human hair, and then do that 100 times over. You expected 3 small solid objects. That is the picture from the textbook. 3 little balls in a bag. There are no balls. There are 3 points of very nearly nothing. Up and down quarks, weighing 2 and 4 mega-electron volts, which is to say weighing almost nothing at all. And they are not sitting still. They are moving at a substantial fraction of the speed of light, because they are confined to a region so small that quantum mechanics forbids them from being slow. Confine something tightly, and its momentum becomes correspondingly uncertain and correspondingly large. The tighter the box, the faster the contents. Between them and around them are the gluon fields, and these are not a faint background. They are the dominant feature. They do not fade with distance the way anything in your everyday experience fades. They pull on themselves, forming tubes and knots and structures, constantly rearranging. And the whole interior is boiling. Free quark-antiquark pairs are appearing out of the field and annihilating back into it continuously, so that the number of particles inside a proton at any given instant is not a fixed number. The 3 quarks in the recipe are a bookkeeping device, the net excess, the balance left over after all the pairs cancel out. They are not a census. Now the number. All of that motion, all of that field tension, all of that energy of confinement and refusal, that is where 99% of the mass around you comes from. Not from substance. From the energy of a system that cannot come apart, at rest as a whole, while everything inside it moves at nearly the speed of light. Your body weighs what it weighs because of something that is happening, not because of something that is there. I want to sit inside that for a moment, because it is the single most disorienting fact I know. If you could somehow switch off the strong force for 1 second, you would not become lighter. You would cease. Every nucleus in your body would come apart, and the quarks would fly free, and the mass would simply not be there, because there would be no bound system for the energy to be trapped in. The 79 kilograms is not a property of your material. It is a property of a process, running continuously in every one of the roughly 10 to the 28 nucleons that make you up, and it has been running without interruption since about 10 microseconds after the beginning of the universe. Now, why did I call this a broken symmetry? Because so far I have described a force, not a symmetry breaking. Here is the connection, and it is where the ball and the hat come back. Alongside the gauge symmetries that generate the forces, the strong sector has another symmetry, called chiral symmetry. Recall chirality, the left-handed and right-handed varieties of matter particles. A theory with exact chiral symmetry treats them identically. Swap every left-handed quark for a right-handed one in any process, and nothing changes at all. If the up and down quarks were exactly massless, the strong force would have this symmetry exactly. And they very nearly are massless. 2 and 4 mega-electron volts is close enough to 0 on the scale of the strong force that chiral symmetry ought to be an excellent approximation. It is not. It is broken, and it is broken spontaneously, in exactly the sense we met in 1964. The vacuum of quantum chromodynamics is not empty. It contains a condensate, a standing, non-zero average of quark-antiquark pairs, filling all space, in the same way the Higgs field has a standing non-zero value. The strength of that condensate corresponds to an energy scale of roughly 250 mega-electron volts. There is a second Mexican hat. There is a second ball in a second trough, and once again, the ball cannot stay in the middle. The consequences are the mirror image of the Higgs case, and the difference is instructive. When the Higgs mechanism broke a gauge symmetry, the resulting Goldstone bosons were eaten by the gauge bosons and became their masses. Chiral symmetry is not a gauge symmetry, it is a global one, so nothing eats the Goldstone bosons. They survive as real particles you can produce in a laboratory. They are the pions. And now, the pion's strangeness resolves. If chiral symmetry were exact, the pions would be exactly massless Goldstone bosons, a quark and an antiquark, bound together with a total energy of precisely zero. They are not massless. They weigh about 140 megaelectronvolts, which is enormous compared to their ingredients, but tiny compared to every other particle the strong force builds. The proton is 938. The pion is 140. That gap is the fingerprint. The pion is light because it is very nearly a Goldstone boson, and it is not exactly massless because chiral symmetry is not exactly broken. The up and down quarks have a small Higgs-derived mass, which tilts the hat slightly, which gives the ball a preferred spot and costs a little energy to roll away from. The pion's mass measures the size of that tilt. It is, in a real sense, the one place in the proton's neighborhood where the Higgs field's fingerprints are directly visible. And then there is the deepest part of the whole business, which physicists call dimensional transmutation, and which I find genuinely difficult to accept even knowing it is true. The equations of the strong force, in the limit where the quarks are massless, contain no mass scale at all. Nothing in them specifies a size, a weight, or an energy. They are scale-free. You could write them down without ever mentioning a unit. There is only a dimensionless coupling strength that changes with the energy at which you probe. And yet out of those equations comes a definite mass, 938 megaelectronvolts, the same for every proton in the universe. The scale appears because the coupling strength varies with distance. At high energies it is small. As you move to lower energies it grows, and there is a particular scale at which it becomes strong enough that quarks can no longer be treated as free. That scale is somewhere around 200 to 300 megaelectronvolts, and it sets the mass of everything the strong force builds. A theory with no mass in it produces a mass, out of the way its own strength changes with distance. Almost your entire weight is the number that falls out of that process, which is a remarkable claim to make, and it raises an obvious objection. How would anyone ever check it? You cannot solve these equations with a pencil. The force is too strong for the usual approximation methods to work, which is precisely the regime where they break down. The answer is that you check it with a supercomputer, and the fact that it worked is one of the finest calculations ever done. The problem with the strong force is that it is strong. That sounds like a joke, but it is the entire technical difficulty. Physicists calculate by approximation. You take the interaction, treat it as a small correction to something you can already solve, and add up a series of increasingly small terms until you have the precision you need. For electromagnetism, this works beautifully, because the coupling is small. It is where the famous 11 decimal place agreements in quantum electrodynamics come from. For the strong force at low energies, the coupling is not small. The correction terms do not get smaller. The series does not converge. The method simply fails, and it fails precisely in the regime where protons exist. So for about 30 years, the situation was this. Physicists were confident they had the correct equations for the strong force, and could not solve them for anything you could hold. The way out was proposed by Kenneth Wilson in 1974, and it is beautifully brute force. Stop trying to be clever. Take a small region of space and time, chop it into a grid of discrete points, put the quark fields on the grid points, and the gluon fields on the links between them, and then have a computer evaluate the theory directly, numerically, point by point. This is called lattice quantum chromodynamics, and what it amounts to is building a tiny simulated universe governed by the strong force and then measuring things inside it. The demands are severe. The grid has to be fine enough that the spacing is much smaller than a proton, or you cannot resolve the structure. It has to be large enough that a proton fits inside with room to spare, or the walls distort the answer. Both of those conditions at once means a great many points, and at every point, the fields have many components, and the calculation involves integrating over all their possible configurations. The computing cost is enormous. The calculations that matter here consume tens of millions of processor hours on national supercomputing facilities and run for years. For a long time it was not possible. Machines were too slow, so people used simplifications that everyone knew were wrong, and the results were suggestive rather than conclusive. Then, in 2008, a collaboration led by Stefan Dürr and Zoltan Fodor published a paper in the journal Science with a title that sounds modest and is not: Ab initio determination of light hadron masses. Ab initio means from the beginning, from first principles, from nothing. Here is what they did. They took the equations of the strong force. They put in 3 numbers, and no others: the masses of the light quarks, the mass of the strange quark, and one overall scale, to fix the units. Crucially, they did not put in any measured hadron masses. The proton's mass was not an input. The neutron's was not an input. Nothing about the results they were trying to reproduce was fed into the calculation. Then they ran it. They used pion masses pushed down toward the physical value, as low as around 190 mega-electron volts, and extrapolated the rest of the way. And they used 3 different lattice spacings so that they could extrapolate to a continuous spacetime rather than a grid. And out came the masses of the proton, the neutron, and the other light hadrons, computed from the theory alone. They matched the measured values to within roughly 2 to 4%, with fully controlled uncertainties. I want to make sure the size of that is clear. A group of physicists took a set of equations describing a force, gave a computer no information about what a proton weighs, and the computer produced the weight of a proton, which is the weight of U, minus about 1%. The mass of ordinary matter was derived, not assumed. There is a detail about how this is done that I find quietly wonderful, and it is worth 30 seconds. The calculation cannot be run in ordinary time. In real time, the quantities being summed oscillate wildly, and the numerical sum refuses to settle. So physicists perform a mathematical rotation that turns time into an extra dimension of space, a trick that makes the oscillations become smooth decays instead, so that the sum converges. The simulated universe inside the computer therefore has 4 dimensions of space and none of time, and the answers extracted from it are then rotated back. It has no right to work. It works. The proton's mass, computed inside a 4-dimensional spatial box in which nothing is happening, comes out correct. 7 years after that first calculation, the lattice groups did something even harder. They computed the difference in mass between the neutron and the proton, the 1.3 mega-electron volts I mentioned earlier, the number that decides whether hydrogen is stable. That is a difference of about 1 part in 700 between 2 quantities, each of which has to be computed from scratch, which means both computations need to be accurate to far better than that, or the difference is meaningless. And it required including electromagnetic effects alongside the strong force, because the competition between charge energy and quark mass is what determines the sign. They got it. The result came out in 2015, with the right size and the right sign, which is to say that the reason hydrogen exists was derived rather than observed. 10 years later, a different group went further and asked where inside the proton that mass actually sits. The result was published in Physical Review Letters in 2018, and it breaks the proton's mass into 4 contributions. About 32% is quark energy, the kinetic and potential energy of those nearly massless quarks rattling around at relativistic speed inside the confinement region. About 36% is gluon field energy, The energy stored in the gluon fields themselves, the tubes and knots holding the whole thing together. About 23% is something called the trace anomaly, and this one has no classical analogue at all. It exists because the scale independence I described earlier, the fact that the classical equations contain no mass scale, is violated by quantum effects. The theory ought to look the same at every scale, and quantum mechanically it does not, and that failure of scale invariance carries energy, and that energy is nearly a quarter of your body weight. And about 9% is the quark scalar condensate, the piece that traces back to the Higgs field, including contributions from strange quarks fluctuating in and out of the interior. Now, an honest caveat, stated once and then set aside. That four-way split is not unique. In quantum field theory, quantities like how much of the mass is gluons are not physical observables on their own. Only the total is. The decomposition depends on a choice of mathematical convention, a renormalization scheme, and an energy scale, and the numbers shift by several percentage points if you make a different choice. The figures I gave are quoted in the standard scheme at an energy of 2 giga-electron volts. This is not a defect, and physicists are entirely open about it. It is bookkeeping, and useful bookkeeping. But if anyone ever tells you flatly that a proton is exactly 36% gluons, they have skipped a step. What is not convention-dependent is the total, and the total is unambiguous. 99% of the proton is energy, and about 1% is the rest masses of its quarks. It is also worth noticing what the calculation does not do, because the distinction becomes the whole point at the end of the night. The lattice tells you that the strong force, given those inputs, produces that mass. It does not tell you why the coupling strength runs the way it runs. It does not tell you why the scale at which the force becomes strong sits at 200 or 300 mega-electron volts rather than somewhere else entirely. And it certainly does not tell you where the quark masses that were fed into it came from. Those were inputs, borrowed from the other mechanism, which cannot explain them either. It is a verification, not a derivation. It confirms that the equations we wrote down produce the world we live in. It says nothing at all about why those equations. It is worth knowing that the proton's mass is not the only property of it that refuses to decompose the way anyone expected. Its spin does the same thing. A proton has a definite amount of intrinsic angular momentum, and the obvious assumption was that it comes from the spins of the 3 quarks inside, adding up. In 1987, an experiment at CERN measured how much of the proton's spin the quarks actually carry, and the answer was around 30%. The rest is in the gluons and in orbital motion. This was called the proton spin crisis, and 40 years later, the accounting is still not fully closed. The pattern is the same in both cases. Look at a proton, ask what it is made of, get an answer that is mostly not the 3 things in the recipe. So the claim I made at the very beginning has now been paid for. Almost none of your weight is made of anything. There is the arithmetic, 9 mega-electron volts of quark against 938 mega-electron volts of proton, verified from first principles on a supercomputer and decomposed into its parts. Take a moment with what that means about the thing you are lying in. Your body is roughly 10 to the 28th protons and neutrons. Inside every single one of them, right now, 3 nearly massless points are moving at close to the speed of light, connected by fields that will not let them go, with pairs of particles boiling out of the vacuum and vanishing back into it billions of times faster than you could ever perceive. That is going on in your hands. It is going on in your bones. It has been going on continuously in most of those particles since about 10 microseconds after the beginning of the universe, and it will keep going after you are gone, in whatever those atoms become next. The weight of a person is the weight of something happening, and here is where you might reasonably expect me to say that we understand it. 2 mechanisms, both confirmed. The Higgs field for the fundamental particles, the strong force for everything else. Between them, they account for the mass of all ordinary matter to a few percent. Case closed. Except that we have now reached the point where I have to start taking things away, and there are 4 separate places where this falls apart. 2 of them are about numbers the theory cannot explain. One is about a mathematical foundation that has never been proved. And one is about the fact that everything I have described tonight applies to about 5% of the universe. Let us take the numbers first, because they are the ones that keep physicists awake. There is a formula for the mass of every fundamental particle in the Standard Model, and it fits on one line. Take the standing value of the Higgs field, 246 giga-electron volts, multiply by a number specific to that particle, divide by the square root of 2. That is the mass. The number specific to the particle is its Yukawa coupling, and this is where the whole structure quietly hands the problem back to you. The electron's coupling is about 3 parts in a million. The top quarks is very close to 1. The ratio between them is roughly 340,000. Now, in the architecture of the theory, the electron and the top quark are the same kind of object. They are both fundamental fermions. They both acquire mass by the same mechanism, through the same field, by the same formula. There is nothing in the structure of the Standard Model that distinguishes them except the value of that one number. And the theory does not predict either value, does not relate them, does not constrain them, and offers no reason why they should differ by 5.5 orders of magnitude rather than being equal, or differing by 3, or by 1 trillion. The full spread runs from the electron at 0.511 mega-electron volts up to the top quark at about 173 giga-electron volts, 6 orders of magnitude of unexplained numbers. There is one number in that list that looks like it might be trying to tell us something. The top quark's Yukawa coupling is very nearly exactly 1, not 1.3, not 0.4, 1, to within the precision of the measurement. In a theory where every other coupling is some arbitrary small fraction, having the heaviest particle sit at precisely the natural value is the kind of coincidence that physicists either dismiss or build careers on. Nobody has established which it is. At the other end, the electron's coupling has never been measured directly at all. In principle, you would measure it by watching Higgs bosons decay into electron-positron pairs, but the rate is something like 1 in a billion, and no collider that has been designed, including ones that exist only on paper, could collect enough of them. The lightest fundamental particle's connection to the field that gives it mass is a number we have inferred and may never observe. Even the middle of the range was a struggle. The Higgs boson's coupling to the muon, which is the second-generation lepton, reached only about 3 standard deviations of evidence in 2020, 8 years after the discovery. Establishing that the mechanism works the same way for the second generation as for the third took most of a decade. And the pattern within them is, if anything, more provocative than the spread. The matter particles come in 3 generations. 3 copies of the same structure, identical in every property except mass. The first generation is the up quark, the down quark, the electron, and the electron neutrino, and everything you have ever touched is made of the first generation. The second generation copies it exactly. Charm quark, strange quark, muon, muon neutrino. Same charges, same interactions, same everything, just heavier. The third generation does it again. Top, bottom, tau, tau neutrino, heavier still. Nobody knows why there are 3. Nobody knows why there are not 2 or 17. Experiments at CERN in the 1990s established that there are exactly 3 generations of light neutrinos by measuring how quickly the Z boson decays. The more neutrino species available for it to decay into, the shorter its life, and the answer came out at 3. So we know the number. We have no idea what sets it. The muon is the one that broke people's patience first. It is an electron in every respect, except that it is about 207 times heavier, and it falls apart in 2 millionths of a second. When it was identified in the 1930s, the physicist Isidore Rabi is supposed to have responded with 4 words that are still quoted at conferences. Who ordered that? Nobody has answered him. 90 years on, the muon is still an electron that weighs 207 times more for no reason anyone can state. And the tau, the 3rd generation version, weighs about 17 times more than the muon, which is not the same ratio, so even the pattern of the pattern does not repeat. This whole cluster of unexplained numbers is called the flavor puzzle, and it is a genuinely uncomfortable thing to sit with. The Standard Model's table of masses is not a law, it is a list. It has the character of the periodic table before quantum mechanics, a set of regularities that clearly mean something, arranged in patterns that clearly are not accidental, with no underlying explanation available. Frank Wilczek has made exactly that comparison, that the mass table looks like pre-Mendeleev chemistry, a set of numbers we are copying down accurately without understanding what generates them. Whether there is a Mendeleev coming, nobody knows. There is a further wrinkle that makes the puzzle harder rather than easier. The masses are not the only unexplained numbers in that sector. The generations also mix. A quark of one generation can turn into a quark of another through the weak force, and the probabilities of those transitions are encoded in a set of numbers arranged in a grid called the mixing matrix. Those numbers are also unexplained inputs, and they are not independent of the masses. The mixing angles and the mass ratios show suggestive numerical relationships that have been noticed for decades and never derived. It is like being handed 2 separate unexplained lists, and then discovering the lists are correlated. Attempts have been made, grand unified theories, which try to fold the 3 forces into a single larger symmetry that breaks at some enormous energy, predict specific relationships between quark and lepton masses. Those predictions work approximately for the heaviest generation. The bottom quark and the tau lepton do roughly converge at high energy in the way the simplest models say they should, and then fail in detail for the lighter generations. Approximately right and specifically wrong is the least useful result a theory can produce, because it suggests the idea is close to something true without telling you what. And then there are the neutrinos, which do not merely lack an explanation, they have mass the theory says they cannot have. In the original Standard Model, neutrinos are exactly massless, and this is not a lazy assumption. It is forced. A mass term needs both a left-handed and a right-handed version of the particle, and only left-handed neutrinos have ever been detected. Right-handed neutrinos, if they exist, do not participate in any known interaction, not electromagnetism, not the strong force, and not even the weak force. They would be essentially invisible. So the theory set neutrino masses to 0, and everybody was comfortable. Then the neutrinos from the Sun went missing. For decades, experiments detecting solar neutrinos found only about 1/3 of the number the Sun should be producing. The favored explanations were that the detectors were wrong, or the solar models were wrong. Neither turned out to be true. In 1998, the Super Kamiokande experiment in Japan showed that neutrinos change flavor as they travel. A neutrino produced as one type arrives as another. In 2001 and 2002, the Sudbury Neutrino Observatory, 2 kilometers underground in a Canadian mine, closed the case by counting all 3 types and finding the total exactly matched the Sun's output. The neutrinos had not gone missing, they had changed on the way. That process is only possible for particles with mass. Takaaki Kajita and Arthur MacDonald shared the Nobel Prize for it in 2015. So neutrinos have mass, and the theory as written forbids it, and the fix has never been observed. How much mass? Almost none. and the measurement is one of the most delicate experiments running. The Katrin experiment in Karlsruhe measures the energy of electrons emitted in the radioactive decay of tritium, with a spectrometer 10 meters across held at an extraordinary vacuum. If neutrinos have mass, they carry a tiny amount of energy away with them, and the very highest energy electrons, the ones where the neutrino got almost nothing, fall slightly short of where they would otherwise land. You are looking for a minute distortion at the very edge of a spectrum. The result published in 2025, based on about 36 million electrons recorded over 259 measurement days, sets the upper limit at 0.45 electron volts. To put that in proportion, an electron weighs about 511,000 electron volts. So a neutrino is at most about 1/1,000,000th of an electron, and possibly far less. The experiment is continuing, aiming for a final sensitivity somewhere near 0.3. The leading explanation for masses that small is called the seesaw mechanism. The idea is that right-handed neutrinos do exist and are enormously heavy, perhaps close to the scale where the forces might unify, and that their great weight pushes the mass of their left-handed partners down proportionally, the way one end of a seesaw goes up as the other goes down. It is elegant. It would explain why neutrino masses are so absurdly small compared to everything else. And there is no experimental evidence for it whatsoever, because the heavy partner is far beyond the reach of any collider we could build. So step back and count what we have. We have a mechanism that explains how fundamental particles acquire mass, and cannot explain the mass of a single one of them. We have a second mechanism that produces 99% of the mass of ordinary matter, out of a theory that contains no mass at all. And we have a class of particle that has mass, the framework forbids, explained by a partner nobody has ever seen. That is 3 of the 4 problems. The 4th is the largest, and it does not concern the particles in this room at all. Stand on a bathroom scale in a dark room and read the number. Now take it apart with everything you have learned tonight. Somewhere around 1% of what that display is reporting is the rest masses of fundamental particles, delivered by a field that has been sitting at 246 giga-electron volts everywhere in the universe since 100 billionth of a second after the beginning. The other 99% is the energy of gluon fields, tension, motion, confinement, a process running inside every nucleon you contain, faster than any clock can follow. That is the number on the scale. But notice what the scale is actually measuring. It is measuring how hard the Earth pulls on you. That is gravitational mass. Now step off and push a heavy door. That resistance in your arm, that is inertial mass. A different property, a different equation. Nothing in Newton's framework, and nothing in the standard model, requires those 2 numbers to be the same. They are the same, and nobody knows why. This is the oldest unexplained coincidence in physics. It has been tested for 300 years with increasing severity. In the 1880s, Laurent Ertfuss built a torsion balance sensitive enough to compare the 2 masses of different materials to about 1 part in 100 million, and found nothing. Over the 20th century, that limit was pushed down repeatedly. And then, between 2016 and 2018, a French satellite called Microscope carried the experiment into orbit, where the 2 test masses, 1 titanium, 1 platinum, could be left in free fall around the Earth for months at a time, with nothing shaking the apparatus. The final result was published in 2022. Titanium and platinum fall at the same rate to within about 1 part in 1,000 million million. 2 substances with completely different compositions, different nuclei, different proportions of binding energy to quark mass, and gravity treats them identically to 15 decimal places. Einstein took that seriously enough to build general relativity on it, and general relativity explains the consequences beautifully. It does not explain the coincidence. Neither mechanism we have discussed tonight has anything to say about it. The Higgs field does not know about gravity. Quantum chromodynamics does not know about gravity. And yet whatever combination of the two produces an object's mass. Gravity responds to the total with perfect indifference to the recipe. That is the first of the remaining problems, and it is the gentlest of them. The second is worse, and it concerns the Higgs boson's own mass. Recall that the boson weighs about 125 giga-electron-volts. In quantum field theory, the mass of a particle is not just what you write in the equations. It receives corrections from every virtual process the particle can participate in, every fleeting interaction with every field it touches, and for a particle like the Higgs, those corrections are not small. They grow with the energy scale at which new physics enters. If the standard model holds all the way up to the Planck scale, which is around 10 to the 19 giga-electron-volts, and is where quantum gravity must take over, then the corrections to the Higgs mass should be of that order too, 10 to the 19. The observed value is 10 to the 2. For the corrections to cancel down to the value we measure, the underlying parameters would have to agree with each other to something like 34 decimal places. Not approximately, exactly, out to the 34th digit, with the leftover being the entire mass of the Higgs boson. This is called the hierarchy problem, and I want to be careful about what kind of problem it is. It is not a contradiction. Nothing forbids a cancellation that precise. The theory works. The issue is that a cancellation to 34 decimal places with no reason behind it feels, to most physicists, like a message that something has been missed. For 40 years, the leading answer was supersymmetry, a proposed symmetry pairing every known particle with a heavier partner whose quantum corrections would have the opposite sign and cancel the firsts automatically, no fine-tuning required. It was elegant, it solved several problems at once, and it predicted partner particles light enough to be produced at the Large Hadron Collider. The collider has been running since 2010. No supersymmetric partners have been found at any of the masses that would make the cancellation natural. So the hierarchy problem is not just unsolved, it is in worse shape now than it was 20 years ago, because the most promising solution has been searched for and not found. Nima Arkani Hamed has argued in public that this negative result is the most important experimental finding of the century so far, and I think he is right, and I also think that is a strange and slightly melancholy thing for a physicist to have to say. The third problem is the same disease in its most extreme form. The Higgs field carries energy even in empty space. That is what a non-zero vacuum value means. So do all quantum fields, through their constant fluctuations. And general relativity is unambiguous that energy gravitates. Energy of any kind, in any form, curves space-time. So the vacuum should weigh something, and its weight should show up as a cosmological constant, driving the expansion of the universe. The universe's expansion is indeed accelerating, and we have measured the constant responsible. When you compare the measured value with the value you get by adding up the expected contributions from quantum fields, the numbers disagree by up to 120 orders of magnitude. 120, that is a 1 followed by 120 zeros. It is routinely described as the worst quantitative prediction in the history of science, and the description is not unfair. The Higgs field's own contribution alone, taken at face value, is off by around 55 orders of magnitude. Something is cancelling those contributions to an absurd number of decimal places, leaving behind a residue that is small but not zero, and nobody has any idea what the cancelling mechanism is. So the field we spent the first half of tonight on, the one that fills space and gives fundamental particles their mass, also predicts a universe that should have torn itself apart before it was a second old. It did not. We do not know why. And then there is the fourth thing, which is the largest, and which makes everything above look like a rounding error. Everything I have described tonight, the Higgs mechanism, the quark condensate, the gluon fields, the whole apparatus, applies to ordinary matter, atoms, stars, planets, you. Ordinary matter is about 5% of the energy content of the universe. Roughly 27% is dark matter. It has mass. That is the entire reason we know it exists. Galaxies rotate too fast for the visible material in them to hold together. Something with mass is holding them. Light bends around galaxy clusters more sharply than the visible mass can account for. In the bullet cluster, two galaxy clusters that passed through each other, the ordinary gas was slowed by the collision and left behind, while the gravitational mass sailed on ahead. The mass and the matter physically separated, and we watched it happen. Whatever that mass is, it outweighs everything made of atoms by roughly 5-1. And it has no explained origin whatsoever. It does not appear to couple to the Higgs field in any way we can detect. It is not bound by the strong force. Direct detection experiments, enormous tanks of liquid xenon buried under mountains, shielded from everything, watching for a single recoiling atom, have been pushing their sensitivity down by orders of magnitude for 20 years. Xenont, Lux Zeppelin, Panda X. None of them has seen anything. The evidence is not thin, which is what makes the silence from the detectors so uncomfortable. Beyond the rotation curves and the lensing and the bullet cluster, the strongest case comes from the oldest light in the universe. The cosmic microwave background carries a pattern of hot and cold patches at particular angular sizes, and those sizes are set by sound waves that traveled through the early universe before atoms formed. The relative heights of the peaks in that pattern depend sensitively on how much ordinary matter was present, and how much matter was present that did not interact with light. The numbers come out at roughly 5% and 27%, and they agree with the completely independent accounting from galaxy surveys and from the abundances of light elements produced in the first few minutes. 3 separate lines of evidence, from 3 different eras of cosmic history, using 3 different kinds of physics, all landing on the same answer. Whatever dark matter is, the case that it has mass is about as solid as anything in cosmology. And there is a possibility worth noting here, because it links 2 of tonight's problems. There is a separate fine-tuning puzzle in the strong force, a term the equations permit, which would give the neutron a measurable electric dipole moment, whose coefficient has been measured to be smaller than about 1 part in 10 billion, when there is no reason it should not be of order 1. A hypothetical particle called the axion was invented in the 1970s to explain that away, and the axion happens also to be one of the better dark matter candidates. It is entirely possible that 2 of the unexplained things in tonight's list have a single answer. It is also entirely possible they do not. Nobody has found an axion either. So take the bathroom scale back out and widen it. Point it at the universe. 5/6 of the matter it would weigh is made of something that has never been identified, has never been produced, has never been detected in a laboratory, and gets its mass from a mechanism nobody has proposed with any confidence. We have spent the night explaining the origin of the mass of ordinary matter, and ordinary matter is the minority. That is 4 problems, and I promised you 4. But there is a 5th thing I have been holding back, and it is the strangest of all, because it is not about physics. It is about mathematics. 99% of your weight comes from the strong nuclear force binding quarks into protons and neutrons. I have described how that works, and I have told you it has been verified numerically to within a few percent by some of the largest computers on Earth. What I have not told you is that nobody has ever proved it is possible. The theory of the strong force belongs to a family called Yang-Mills theories, and there is a mathematical question about them that has never been answered. The question is whether a quantum Yang-Mills theory rigorously exists as a mathematical object at all, and whether it has what is called a mass gap, a lowest possible excitation with a strictly positive mass, rather than states extending all the way down to zero energy. The mass gap is the formal statement of why the strong force is short-ranged and why the things it builds have mass. It is why a proton weighs anything. In the year 2000, the Clay Mathematics Institute named 7 of the most important open problems in mathematics and attached $1 million to each. Yang-Mills' existence and mass gap is one of them. 26 years later, it is still unclaimed. Physicists are entirely confident it is true. Experiments show it. Lattice simulations show it. The world you are lying in demonstrates it continuously. But the mathematical foundation underneath 99% of your body weight is, formally speaking, an unproved conjecture. So let me put all of it together, because this is the answer to the question in the title, and I want it stated plainly. The first hole is the values. The Higgs mechanism explains how a fundamental particle acquires mass, and does not explain the mass of a single one. Every fermion mass is a free parameter, measured and typed in. The electron and the top quark are the same kind of object in the theory, and differ by a factor of 340,000 for no known reason. The mass table is a list, not a law. The second hole is the mechanism's own foundation. The Mexican hat shape of the Higgs potential is assumed rather than measured. The 246 giga-electron-volt vacuum value is measured, not derived. The boson's own mass of 125 giga-electron-volts is measured, not derived, and appears fine-tuned to 34 decimal places against corrections that should have made it enormous. The third hole is the 99%. The strong force account of your mass is verified numerically and unproved mathematically, and the scale that sets the proton's weight, that 200 or 300 mega-electron-volt threshold where the coupling becomes strong, is itself just another number we measured. The fourth hole is that all of this concerns 5% of the universe, and underneath all 4 sits the oldest question in the subject, which is the one physics is structurally worst at answering. Why is there symmetry at all, and why does it break? Symmetry is the deepest organizing principle we have found. It generates the forces. It produces the conservation laws. It constrains the shape of the equations so tightly that once you commit to it, most of physics follows. And the universe exists only because that principle is violated. Perfect symmetry gives you nothing. Massless particles, moving at the speed of light, forever, in every direction, never slowing, never binding, never forming a nucleus or an atom, or a molecule, or a star, or a person. A universe in perfect symmetry is a universe in which nothing can ever happen twice in the same place. Everything that exists because a ball could not stay in the middle of a hat. Twice. In 2 completely different parts of physics, at 2 different moments in the first 10 millionths of a second, a symmetric configuration turned out to be unstable, and the universe tipped to one side. The first tipping gave the electron its mass and made atoms possible. The second gave you 99% of your weight. Physics can date both of those events. It can describe their consequences to 11 decimal places. It can compute the outcome on a supercomputer without being told the answer in advance. It cannot tell you why either of them happened. Physics is very good at how, and almost silent on why. I said that hours ago, before you had any reason to take it seriously, and it is the honest diagnosis of everything we have looked at since. There are proposals, and I want to name a few of them, with the label attached. These are speculation, not established physics, and none of them has produced a prediction that has survived a test. One family says the Higgs boson is not fundamental at all. If it is a bound state of some new and more fundamental hidden constituents, the way a pion is a bound state of quarks, then the fine-tuning problem largely dissolves, because a composite object's mass is protected by the scale at which it is held together, rather than running away to the Planck scale. Nature would then have used the same trick twice, and the thing we call elementary would turn out to be another proton-like knot in something we have not met. These models predict small deviations in how the Higgs couples to other particles, which is precisely what the collider will be looking for over the next decade. Another family says gravity is weak because it leaks into spatial dimensions we cannot see, which would move the true fundamental scale down to the reach of existing machines and remove the hierarchy problem entirely. That was searched for extensively. The simplest versions are now excluded. And a third position, held by serious people and profoundly unsatisfying to almost everyone, including the people who hold it, is that the Higgs field's value varies across an enormous landscape of universes, and only a narrow band of values permits stable atoms and long-lived stars, and therefore the value we measure is not a derivation but a selection effect. We measure 246 giga-electron volts because observers can only exist where the number is close to that. It is not obviously wrong. Steven Weinberg used exactly this kind of reasoning in 1987 to put an upper bound on the cosmological constant, and the value measured a decade later fell inside it. But an explanation of that shape ends the conversation rather than continuing it, and it is very hard to test. I do not want to leave you with the impression that the work has stopped, because it has not, and some of it is being built right now. At Brookhaven National Laboratory on Long Island, a machine called the Relativistic Heavy Ion Collider completed its 25th and final run in February of this year, and engineers began taking it apart. Its tunnels and infrastructure are being reused for something called the Electron-Ion Collider, a machine designed for exactly one purpose, which is to photograph the inside of a proton. It will fire polarized electrons into polarized protons and heavier nuclei, and map where the quarks and the gluons actually are, and how they move, and how much of the mass and the spin each of them carries. The Department of Energy approved the next phase of funding earlier this year, and conventional construction began this spring. It will cost somewhere between $1.7 and $2.8 billion, and it will start running in the first half of the 2030s. It will not tell us why the Yukawa couplings are what they are. It will not prove the mass gap, but it will let us look directly at the process that supplies almost all the weight of everything, instead of inferring it from a simulation. That is worth building. So here is where we end up. You began tonight with a number you had never questioned. It turns out that number is not a measure of how much of you there is. It is a measure of how much energy is trapped in the arrangement that is currently you. Energy in fields that will not let their contents escape. Energy of motion that has nowhere to go, running continuously in every particle of your body since the universe was 10 microseconds old. Almost none of your weight is made of anything. What it is made of is a process that has been going, without interruption, for 13.8 billion years, and will keep going in those same particles long after they stop being you. And the reason we cannot fully explain it is not that we have not looked hard enough. It is that every explanation in physics converts one set of unexplained inputs into a smaller and more fundamental set. Mass has been pushed down 2 levels, from substance to field, from field to symmetry breaking. It has not been eliminated. It has just been moved somewhere harder to reach. Thank you for staying with me through all of that. If this kind of slow walk into a question is something you enjoy, a like or a subscribe genuinely helps this channel keep going, and it means a great deal to me. And remember, the next time you step on a scale, almost every gram of what it tells you is something happening rather than something there. Good night, and may you never quite look at your own weight the same way again.